Disgusting.
All right, what we're going to cover today, last thing, same as last chapter. Hypothesis testing for variance and standard deviation. Last chapter, variance standard deviation was the last part of or last section of the chapter. Same idea here. So what we're going to be doing, finding critical values for. Does anybody remember what that symbol is?
Chi-squared.
Chi-squared. All right. So chi-squared test. So instead of doing your z-test like we've been doing, chi-squared. You asking about which one?
Yeah.
One of y'all is wearing something I'm allergic to.
Tell them again, Gage. Everybody listen. Shh. Gage, tell them again. P-hat. Sample proportion. P-hat means sample proportion, same as X-bar. Remember I've told you on all these, do I accept X-bar as an answer? No, X-bar is just the symbol itself. What's X-bar mean, or what's it tell you? Mean of sample. P-hat means the proportion or the percentage of a sample. Use the chi-squared test to test the variance standard deviation. That's what we're going to be doing. In real life, it is important to produce consistent results. These are the kind of tests that if you guys all went, I don't know how much they showed you and stuff, but if you went on that field trip last week, did they really show you anything, or did they show you around the plant? Did they explain anything to you?
They showed us some stuff.
Did they explain to you stuff like, you have to be within this amount on when you're making this or anything?
Oh yeah, a dude from Timken Steel told us that they have to make lines down to like the
Yeah.
something, the kilometric.
So this is what they use, or what they're probably not the people that the people who are working there probably can't explain to you what it is, but this is what the computer uses. All right, the computer says, hey, we need to be within this range, whatever it is. Otherwise, I need to kick back that something's screwing up so that it can be fixed on the machine. Now, the bad thing is if the computer's the only thing that knows when it's messing up and the computer screws up, then you're just sort of out of luck. All right, so you need to, this is why people need to know too, hey, what am I doing here? What's the computer doing here, and is the computer still okay? Things like golf balls, bags of chips, car parts, golf balls. Anybody have any idea why would you need to know something about a golf ball? Well, the divots are always going to be the same because that's a press. That's not going to change.
How far it goes.
So what happens?
So like,
The weight.
There's like a center, like you put a line on it, and it has to be a center point.
Right. It's got to have a certain weight. Here, not too long ago, a whole bunch of pros got in trouble because they were using balls that weren't legal. Well, why were they using those balls that weren't legal? They go further and stuff, and
Better distance control.
I never did hear what came of it, but I heard, one guy was about ready to punch out the other guy or something at the end of the match because they figured out that he was using balls that were weighted more or less, whichever one made it go further, and some different kind of setup. So the balls all have to be the same weight, same circumference, same area on the outside, surface area, so on and so on. Bag of chips. With the bag of chips, why would you need to know that?
Well, not every single bag of chips is the same amount, but they have the same amount of weight.
Right.
Serving size.
Serving size and stuff that the government makes them put on there. Now, with a few years ago, so you guys probably won't remember it, but some of the chip companies and the candy bar companies got in trouble because the federal government allows them to be within a certain amount. So if you look at a bag of chips and it says it's 2.5 ounces, there's probably not 2.5 ounces in there. But it's within a range. It's within a variance of that. And what the chip companies and the candy bar companies were doing is they were making sure that they stayed on that lower side. So you're supposed to be, like if we're on our normal curve, you're supposed to be in this range right in here. That curve's terrible, but you're supposed to be in this range. Well, they were staying as close as they possibly could to that end, because it saved them money. That makes sense, right? So if it's supposed to be 2.5, maybe they let them go down to like 2.2 and up to 2.7. It should be in that range. Well, they're not going to screw up towards this way because that's cost them more money because they're putting out more chips. So they were trying to stay, or maybe 2.8. They were trying to stay way down here, and then all of a sudden they were staying way down there for a while, and then they got just outside of it, and they stayed there for a long time too until somebody finally caught them, and then they got in trouble. And
It's kind of crazy that somebody caught on to that.
Yeah.
now,
Just bag of chips.
Man, these don't weigh.
This don't look right.
well,
You like-
I'm sure there was some consumer advocate group. You see all these on the internet, these consumer advocate groups that tell you, hey, this company's good, this company's bad, so on, so on, so on. It was one of those groups that caught them. And now if you look at it, what they've done, instead of doing that, if you compare a candy bar from 15 years ago to a candy bar from now, instead of saying, okay, we need to add more to it,
They get rid of it.
they just changed what it says on the package, and now instead of 2.5 is the weight, now the weight's 2.2. And they moved it down to there so that now the range they have to be in is something like that instead. So when you look at the bag of chips and stuff, and this another thing with chips that always kills me that people don't know. When you buy a bag of chips, there's a whole lot of what in there? Air. Do they do that to try to trick you?
No.
Ain't got nothing to do with trying to trick anybody. Does anybody know why there's a whole bunch of air in there?
Isn't it like nitrogen or something? So it keeps the
Keeps them fresh, that's one of the things. There's one other thing, one other reason. They're not crushed. They put air in there so that when the people are hauling the chips around and packing them in the boxes that they get sent out to wherever, the stores and everything, the air keeps the chips from all being crumbled up. If they didn't put that air in there, then by the time you got the chips, they'd all just be
It's like
little
Cheetos are always crumbling up.
crumbs.
Some of them are just unreasonable though.
I've opened a bag of chips and got like 3 chips.
But
Exactly.
but if it's it can't be.
I'm not saying packaging the like brim, but come on, man.
But it's not unreasonable because they tell you right on there how many ounces it is. So
Give me 2 colors.
if it's unreasonable just because one bag looks like this and the next bag looks like
No,
this,
Same size bags.
but if you look in there, well then that goes back to the weight. All right? But some bags look this size and some bags are this size and they might be the same weight, even though they're 2 different sizes. Just depends on
You know, like
the
them
kind of chips.
Little school ones, like little lunch ones they have.
Yeah.
I've seen like open them and eat normal chips. I've seen Nick open it and get 2 chips.
Yeah, well, and those,
Those are just like.
if you look at the weight on them, it's like 1.2 ounces or something. There's not supposed to be a whole lot in there, so it doesn't take much.
Or it's gonna be more than
They're reduced fat, man.
No, it was because he was like, bro.
All right, what we're gonna do?
3 Doritos ones. Like,
This tells you. Let me move this. Finding critical values for chi-squared test. I would write these down. This is a little tougher on this than it is on the Z and the T stuff. You actually have to do some work with the alpha instead of just looking at the charts and figuring it out from there. other thing I should say, your grade for the 9 week, if you're not happy with it, the test grade on Friday could really help, right? The bad thing is, Johnny sitting here has like a 80 right now. I got an 80, I don't care. And does really crappy on that test. Could also do what?
Bring it in.
Bring it down, and there's counts as a test grade, so it's pretty big a grade.
60%.
It's like 20.
I had the syllabus.
It's not bad.
It's like 15% of my grade.
Do we? So I would highly suggest trying to do as well as you possibly can.
Just do like pretty average on it. You'll be alright.
So your grade doesn't fall any.
Think I'm gonna continue to be a C student and just get a C on it?
I hope you're right, I just hope you don't think you're gonna get a C and all of a sudden get that.
Go for a higher.
I hope my
grade.
D can come up to like a
Shoot
C.
for like a C plus or
Good.
something.
I think
Maybe
that's
a B
better than a
minus.
C. That's a good one.
It's been like a 66 for the last.
No, my issue is every time I leave a test and say, oh, I got it. this is
I got a
so
48
bad,
on that
it
one
works.
test.
Every time.
And then for the whole
I haven't done too
whole
bad.
9 weeks, it's been like chilling at that, like, man, you're barely making it.
One test I missed, and came back.
C's good.
But like, he hasn't graded homework in like 8 months.
I have one.
The homeworks haven't been graded in like 8 months. If I go in there right now, dude, the homework's getting graded.
I opened like super current.
You know, 'cause my grade's been the same since last week. Unless something's happening to keep my grade in the exact same spot.
I heard from somebody that grades got put in today.
They just literally just got put in. Because I'm sitting at a nice 71 right now.
First of all, I don't know what Ben is talking about, because there was only 2 homework grades that I hadn't put in up before today. And then I put in those 2 quiz grades today also. So I don't know how he's saying I haven't done anything for a long time, because this is the one class that I have kept up the whole time. Now, my geometry people, they can complain at me because I've been lazy on that.
I'm gonna look at this real quick. Page 332.
Number 1, specify the level of significance. Again, you're just gonna find alpha. They're gonna tell you what it is, but you gotta do that. Determine your degrees of freedom. Remember, degrees of freedom is just n minus 1. Then what makes this a little tougher than the others? You've got to do one of these 3. And you've got to remember that on the chi-squared chart, which is table 6, it's in your packet. On that chart, it is backwards from everything else we do. Because the other charts tell you the area to the left, the chi-squared tells you the area to the right. So when you're finding a right tail, this one's easy. You just use the chart. Just number on chart. When you're doing a left-tailed, you got to take the number on the chart. Or actually, when you're doing a left-tailed, easiest way is 1 minus this, and then find that on the chart. So 1 minus alpha, and then you got to find that on the chart. And when you're doing a right-tailed, or I'm sorry, 2-tailed, then you have to take half of alpha. You're going to put half of alpha on one side, half of it over here, and the other half over here on the left side, or on the right side. And you just got to look up those 2 numbers. And actually, I just marked them backwards. That should go over there, and then this one actually goes over here. But you'll figure that out, because one of them's going to be bigger than the other. And we'll do a couple of those just to show you, just to make sure you understand it. that bottom one. And actually your chi-squared doesn't, remember, your chi-squared doesn't look the same as the other graph. Your chi-squared looks like this, where it's got a tail on that side. So we're finding the critical values here and here. And we're gonna look them both up on the chart. For the one side, you just take half of alpha. So if alpha is 0.01, that would be 0.005. We're going to use that number and our degrees of freedom, and we're going to look up this critical value on the chart. And then we take this number, just like we did last time, and we subtract that off from 1, and we get 0.995, and we use that number and the degrees of freedom to find that. Actually, put that backwards. That one goes there, that one goes here.
These are sick. I told you.
Phoenix has got me all
What am I doing back here?
discombobulated.
Got you all flustered.
Got me flustered, telling me I haven't been keeping up on my grades.
Yeah, I think you've been doing just fine on the grades.
You've been doing great on the grades, now that it's actually upgraded. Thank you.
Phoenix, he's also feeling very ill today. He should be. The Pope told me. The Pope told me,
There.
cause he was coughing whenever you.
Hope said I could make this into the 700.
So this is
700.
This is half of alpha, this is half of alpha. 1 minus alpha is in here. We're gonna look up and have a chi-squared left and chi-squared right again, like we did last chapter for our two critical values. It's not as hard. Last time we had to do all this, last chapter we had to do a big calculation for it. This time we're just using the chart to find them.
You ain't gonna do it. I think I'll know somebody. Oh, yeah, I should do it.
So to find these, have out the chart so you can help me find them.
I missed.
What were you shooting at?
The 100, 300 thing.
Go pick it up.
Can I dunk it?
No, put it in the trash can. This is just, end of the 9 weeks here. And when we do seating charts this next 9 weeks,
I'm hoping they're good.
I didn't think
it's most definitely not gonna be letting everybody set where they wanna set,
Can I
right?
at least be in like the middle so I can see the board?
Yeah, we'll see.
Ben Derry would do that.
I just don't want to be in those
I did not dare to do that.
Find the critical value, chi-squared, for a left tail test when n equals 11 and your output is 0.01. So on the left tail, we're like this. We got our chi-squared, left tailed, we're over here. We're trying to find this critical value right here is what we're looking at. Remember our curves for chi-squared again, not the same as the normal curve. Everything's positive on the chi-squared curve. All you do with this is on your chart, you find your degrees of freedom. What's your degrees of freedom this time? 10. And we use that 0.01. So you go to the chi-squared chart. And I highly suggest that you got your charts out so you can do this right now. Chi-squared chart.
Where is that?
It's
10.
it's chart number, it's table 6. It's right before, like this chart that we've been using a whole bunch.
There it is.
23.209.
Where's it at?
It's like right before that chart.
Say.
Looks like this,
Ben, this one.
table 6.
Yeah.
Yeah.
It's right after 55.
The very last one before this.
This one?
Table 6.
Yeah, this is table 6.
Good job.
Everybody see it?
Yeah.
So on it, we're going to go down to 10 on the side, and we go over to, I'm sorry, this is wrong because we're doing a left tail. If we were doing a right tailed, I thought I did a right tailed first. If we were doing a right tailed, we would just go over to 0.01. Since we're doing a left tailed, you got to do this. You got to take 1
minus
minus your alpha, what's that give us?
0.09.
0.99.
Yeah.
Alright, so 0.99. So we go 10 and over to 0.99, and what's it tell us?
2.558.
2.558. That's our critical value, 2.558. If it was right-tailed, alright, if it was right-tailed, then we wouldn't do the subtraction. We would just find that, and it would be, what is it, like 23.209? That would be over here somewhere, but this one's just that one this time. I even wrote that down there so I could not forget that, hey, I didn't do it right tail, I did left tail. I still forgot. So we have a chart that looks like that. Remember, your chi-squared's not the normal curve. 2.558. That's our critical value. This is our rejection region. For a chi-squared value for a two-tailed test, what's our DF on this one? 8. And we got 0.05. The first thing you got to do with 0.05 is you got to take half of it. So somebody help me out. What's half of 0.05? Say it again. 0.025. And what we're going to do, oops, got my 0. What we're going to do with that, we got 0.025. We also want to subtract that from 1. Make it easy on yourselves. What's 1 minus 0.025? Can anybody do that in their head? Close. Got the first number. 0.975. All right? So those two numbers, we take this and this, look it up on the chart, then we take the 8 and the 0.975, look it up on the chart, and this time we're going to have two-tailed. So we're going to have a tail over here and the tail over here. So this critical value, that critical value. So look up this one first. 8 and 0.025. What's 8 and 0.025 give us?
17.535.
You think that goes over here or over here? Is that left or right?
Probably on the right.
So what'd you say, 17 point what?
535.
Anybody else get that? And then we do 8 and 0.975. What's that give us?
2.180.
So this is our critical value on that side, that's our critical value on that side. That's a rejection region, that's a rejection region. Then what we do from there is the same thing that we've been doing. We're going to do our HO, our HA, do all that stuff, decide whether to reject or fail to reject the null, and that's one thing I will say on the quiz. Several of you are trying to write whether you reject or fail to reject the null in your sentence. Don't do that. It doesn't go in there. All right? So one of the answers on the test is reject, and this doesn't work for this problem or anything, reject the null. That's a completely separate answer from you writing out your interpretation. All right? That comes before. It's completely separate. So if we did all this right, hopefully it did the degrees of freedom correctly. Okay, we got 2.180 and 17.535. So those are your two critical values using the chart here. What we're going to do on this part right here, I for sure would write down. That's the formula that you're going to be checking. That's like your Z or your T that we've been doing up to this point. That's what you're going to check, see if it falls in the rejection regions. When we do the test, the rest of it, I probably wouldn't write down the rest of it. Just know that what you are testing is your S squared. What is S squared? Somebody tell me what S squared means.
Standard deviation.
That's your variance.
Variance of,
Well, the sample, my bad.
variance of the sample. So we're saying, all right, if we're testing the variance of the sample, then this is the formula we're gonna use. So if you're testing the variance, this is the way we do it. Again, make sure, what's this right here? Chi squared, not x squared, chi squared. Right, Brendan?
Absolutely. We need to know. Absolutely.
I've already been that little speech that I made at the beginning didn't matter. About the end of the 9 weeks and so how this test could.
Make or break your game.
So what we're doing here, we're using chi squared to test your variance or standard deviation. This is for standard deviation for variance. If we're testing the variance, we use this formula. N minus 1 in the formula is just your degrees of freedom. S squared. Sometimes they'll tell you S squared, so they'll tell you the variance of the sample. If they tell you S squared, then you just put that number in there and you don't square it again. We had this trouble last chapter at the end there because sometimes they tell you the variance, sometimes they tell you the standard deviation. If they tell you the standard deviation, then you stick that number in there and you have to square it. If they tell you the variance, then you just stick that number in there.
I think I've written that equation down like 4 different times.
Yeah, it's sort of the same one. Steps to do this. What we're going to do. Number 1, same thing. Number 2, figure out what your alpha is. Number 3, this time you're finding your degrees of freedom. Number 4, use table 6 to find your critical values. Again, if I was writing this down, I'd write down the steps out here on this side. Not worrying about all of this over here so that you don't have to write so much. Know how much you guys love to write.
My favorite.
Use Pylon 6.
Do what?
So use table 6.
So just about everything that we've done this chapter, basically the same stuff over and over again. You're changing that little formula to check, see where you, what your test value is, what you stick into to see if it falls in the rejection region or not. But this first part, state the null, alternative hypothesis, that's the same. Figure out your level of significance, that's the same. Degrees of freedom changes, because we haven't used degrees of freedom on all of the other stuff. We did use it on the T-chart one last time. So that, or 2 times ago, think on this test, you might put section 7.5 or something that started these notes. Because on this test, I think I even left it on the test. Hey, this goes with section 7.1, this goes with section 7.2, just to try to make it easier on you. I'm not trying to make it difficult. I like it to be easy, but it doesn't always work out that way, right?
That's right.
You know, Leah's saying, well, you could make it easy just by not making us take the test. No, that's not a
I mean, that,
thing that we can do.
that's a true statement.
Okay. Next steps, and I'll write this over a side here in a second. Number 5, draw your little curve, and don't draw that curve. Draw the chi-squared curve, ignore that extra bar going through there. Number 6, figure out that number that you're testing. Number 7, decide whether to reject or fail to reject. And then number 8, down here I'll write it out again. First part, level of significance, so you say with a 1% level of significance or whatever it is. Second part, you get from the chart. And the third part, you tie to the problem.
Yeah.
Sorry, looks like I let Ryan write this. Except it's almost legible. When you take the test, several of the problems on the test, if it's one of the long problems, I think every one of them I have broke up like you had on that quiz. Write the non-alternative hypothesis, tell which one's a claim. Second one, do this. Third one, do this. I think on the test I got, the problem that says part A, do this. Part B, do this. Part C, do this. So if you're following these steps, it just follows these steps right down through. Jackie, this is slide 11 of 101.
It's exciting. When I get to 15.
I'll keep on with number 4.
46, stick with.
Love your kids too. Rosemary.
For time
Yeah. That's scary.
Example here, a dairy processing company claims that the variance of the amount of fat in the whole milk processed by the company is no more than 0.25. You suspect this is wrong and want to find that a random sample of 41 milk containers has a variance of 0.27. At a level of significance of 5%, is there enough evidence to reject the company's claim? Assume the population is normally distributed. Let's do it out here to the side so that we can keep this up here. First thing we're going to do every time, if you're watching this is exactly what the test is. Not exactly, I shouldn't say that. Exact kind of problem that's on the test. So we write our HO, our HA. We look at the claim. It says a dairy processing company claims that the variance of the amount of fat in whole milk processed by the company is no more than 0.25. What's no more than, tell us?
It's equal to or less than.
It's equal to or less than that, right? So is that going to be our HO or HA? HO. So it's less than or equal to 0.25, is that what it said? What's the symbol that goes here?
Sigma.
What are we dealing with here?
Variance.
Variance. So it's sigma
Square.
squared. So make sure, that's another thing I'll mark wrong if you don't use the correct one. Last time we had p's, this time we got sigma, squareds, before that we had mu. All right, make sure you're using the right one. What's our alpha, or our alternative gonna be, not our alpha?
Variance is greater than 0.25.
And what I forget again, that I always forget.
The claim.
Make sure, mark which one's the claim. That one's the claim. So that's 3 points. Now, the next thing we do, would figure out what alpha is. What was alpha this time? All right, and this time we also need to find the degrees of freedom. I think that's the next thing, right?
40.
So it's 41 minus 1, which is 40, Gage says. Then you're going to use these two. First, we look over here. Look right there, and that tells us, are we left-tailed, right-tailed, or two-tailed?
Right-tailed.
Right-tailed. So we draw our little graph, we're right-tailed. If you're right-tailed, all you're going to do is look up this number and this number on the chart. So somebody help me out. What's 40 and 0.05 on the chart?
55.758.
55.758. Anybody else get that? That's our critical value there. Draw this. All right, that's step 5, drawing that.
Then put it in the formula.
Then we got to find
Chi-squared.
the chi-squared value, right? What was on top for the chi-squared?
A minus 1.
You're
So
great.
40.
So 40 times
Standard deviation.
standard deviation. Did they tell us the standard deviation this time? Or not standard, did they tell us the variance this time? Variance of the sample.
0.27.
0.27 over what?
Variance of the population.
Variance of the population, which was what?
0.25.
0.25. Type all that into your calculator. Somebody tell me what you come up with.
43.6.
Anybody else get 43.2? Yes, no, maybe? Then we check that. Does it fall in the shaded region or the not shaded region?
The non-shaded range.
Not shaded region. So next thing, what's that tell us?
We gotta reject that.
Fail to reject the null.
That's just what simple steps.
Alright, so again, all of this, 3 points here, 2 points here, we're drawing this, point here for finding your chi-squared, point here for telling whether you reject or fail to reject the null. And then the last step, what's the last step?
Interpret.
Interpret. We got 3 parts. So I'm going to say with, what was our alpha?
0.5.
5% level of significance. There is the way the next part starts. Get out the chart. Again, we're using that chart. Our claim was it the null or alternative? It was the null, so we look at the first column, and we said fail to reject, so we go down. What's it say? There is not enough evidence to reject the claim. Then the last part, you have to tie it to the sentence. What was the claim?
That the variance of the amount of fat and whole milk processed by a company has been more than 0.25.
That the variance of fat, is that right?
Yeah.
Is,
Whole milk.
or in, how come I wrote 4 instead of fat? Variance of fat in whole milk
Is no more than 0.25.
no more than 0.25.
That's what I'm doing too.
27.
So I said 15.
Yeah, I know.
I was a little off.
It's crazy.
But none of you, if none of you had any idea at that point that I was off, you all just agreed with me.
I do not remember us agreeing with you.
Yeah, you didn't disagree with me. Let
Oh,
me
we
say it
failed
that way.
to, you know.
You
reject
failed,
your-
right, you
Yeah.
failed to reject my
Claim.
claim, my hypothesis. Yeah. Let's see if we did all this right. Is that what we had was 55.758?
That's what numbers up there.
And we came up with 43.2 is our chi-squared. Failed to reject, we did that. At a 5% level of significance, there's not enough evidence to reject the company's claim that the variance of the amount of fat in the whole milk is no more than 0.25.
It's nice they didn't share that though.
Yeah, I know.
Next one, a company claims its standard deviation of lengths of time it takes an incoming phone or telephone call to be transferred to the correct office is less than 1.4 minutes. A random sample of 25 incoming telephone calls has a standard deviation. Notice this time it says standard deviation of 1.1 minutes. At alpha 0.10, is there enough evidence to support the company's claim?
Yep.
Assume that the population is normal. You guys all know this stuff so well, we should just take the test today, shouldn't we?
No, it's pretty good.
Maybe tomorrow, I was about to say, yeah, review
Then
today.
all the chatter needs to quit. A company claims that the standard deviation of lengths of time incoming call to be transferred to the correct office is less than 1.4. HO or HA? HA. And this time, instead of sigma squared, what are we going to use? Just sigma, right? And it's less than 1.4. That's the claim. What's our HO then?
Sigma is greater than or equal to.
Figure out your alpha. What's your alpha?
0.10.
What's our degrees of freedom?
4.
Next thing we're going to do, grab your charts for me. Look at the chi-squared chart. This time we left-tailed, right-tailed, or two-tailed? Left-tailed. Remember, left-tailed this time, it's different because what you have to do to get left-tailed is you got to take 1 minus 0.10. What is 1 minus 0.10? And we use that and 24 to find the number on the chart. So use those two. What's our critical value?
15.659.
Anybody else get that?
Yep.
Now we gotta find our chi-squared that we're testing. Gotta be careful here too, because we're dealing with standard deviation instead of the variance. So DF, what's our DF? 24 times, remember this is supposed to be S squared. Well, when we did this, we figured out that the standard deviation was 1.1, so what are you gonna have to put in here? 1.1, and this time you have to square it, all right? Because this was standard deviation that they gave you, not variance. What goes on the bottom?
Sigma squared.
Sigma squared, right? So what is sigma this time? Remember that comes from 1.4, and we have to remember to Square it this time. Plug all that into your calculator and see what you come up with.
14.816.
Anybody else get that? Yes, no, maybe? What do we do with that? See where it falls. Where does it fall at? Shaded or not shaded? In the shaded? So what's that tell us? Reject the null. It's one of our answers. Instead of me writing all this down this time so we can get on to the next problem, what's the first part of your sentence gonna say?
With 10%.
With a 10% level of significance. Now on your chart, look up on your chart, was the claim, was it the null or alternative this time? The alternative, so look,
There's enough evidence to support the claim.
there is enough evidence to support the claim that, what was the claim?
Standard deviation of whatever.
Time to be transferred is what? Is less than 1.4 minutes. Make sure you can write all that out. See if we did it all right. Is that what we got? Alpha was that, DF was 24. 15.659, is that what we had? And it was left-tailed?
Yeah.
14.816, is that what Elizabeth told us? Reject the null, is that what we said? And 10% level significance. There's enough evidence to support the claim that the standard deviation lengths of time it takes an incoming telephone call to be transferred to the correct office is less than 1.4 minutes. Last one here, sporting goods manufacturer claims that the variance of the strengths of certain fishing line is 15.9. A random sample of 15 fishing line spools has a variance of 21.8 at alpha at a level significance of 0.05. Is there enough evidence to reject the manufacturer's claim? Assume that it's normally distributed. This time, what's our HO and HA?
HO is sigma squared equals 15.9, and that's the claim.
Does everybody agree with that? Yes, no, maybe?
Yes.
This time it just says is 15.9, right? So their claim's wrong even if it's better than that or worse than that. What's our HA then?
That's not equal.
What's our alpha?
0.05.
DF?
14.
For this one, watch closely on this one. Left-tailed, right-tailed, or two-tailed? Two-tailed. You want to make sure, because this one's a little tougher. This one's two-tailed, so make sure you're watching. Two-tailed, on your chart, you're going to look up 1/2 times alpha and the DF, which is 14. What is half of alpha? Got 0.05, what's half of that?
0.025.
0.025. And you're going to look up 0.975 and 14. So somebody look up those two for us, 14 and 0.025. Remember, this is on the chi-squared chart.
26.119.
You think that's our right or our left?
Probably right.
26 point what?
119.
119. Anybody else get that?
Yeah.
And then look up 0.975 and 14.
5.629.
Make sure this should be the smaller one, that should be the bigger one, right? So your left should be smaller, right should be bigger. sort of goes backwards to what your numbers are here. This is the smaller, that's the bigger. They sort of get switched around when you put them on the chart. Chi-squared, DF is 14, so 14 times our S squared. What was our S squared this time? Did they tell us the S squared this time? $21.8. Do we have to square it? No, because this is the variance, right? So it's already squared. On bottom, what's our sigma squared? That comes from right here. Don't have to square it. Do that math. What's that give you? Anybody else get that? 19.194?
Yeah.
We check that. Where does it fall at? Not in the shaded region, so what's that tell us? Fail to reject.
There's not enough evidence to.
Slow down, slow down.
Sorry.
Fail to reject the null. First part of the interpretation is going to say what? With a 5% level of significance, then we look at the chart, and what's it say?
There's not enough evidence to reject.
There's not enough evidence to reject the claim that, what?
Variance of the strength of certain efficient line is 15.
So we're saying there's not enough evidence to reject the claim that the company made that the variance is 15.9.
I have the chart in my head.
Dude,
I get that. 129.
I hope you were right.
Mono.
He's not right.
He's not? That looks like everything we did right. Those two critical values, what we had. 19.195, that's pretty close.
I don't round ever.
Fail to reject, that's what we said. And then our interpretation, hopefully, now that Riley said he did it in his head, I want to make sure here, there is not enough evidence to reject the claim that the variance, is that what you said? That's not. That's your assignment.
Hey,
Page 410, sorry I lied to you earlier, I said page 409.
Don't worry, Ben told me right. I just knew. He just knew.
You're right.
You're well within your rights.
Yeah.
No, you're
Except
not.
what you think. Yes, I am.